What if you could build a different kind of internet? One without the giant banks or big tech companies sitting in the middle of everything. Well, that's the big promise of blockchain. So today, we're going to break down this powerful idea and build it from the ground up, starting with the one single problem it was designed to solve. Think about it like this. If I hand you a $5 bill, I don't have it anymore. It's yours. Simple, right? But digital stuff is totally different. I can copy and paste a photo or send the same email to 100 people. So the real question is, how do you make a digital dollar that someone can't just copy and spend over and over and over again? And that right there is what we call the double spend problem. It's really the biggest hurdle for any kind of digital cash. For decades, the answer was always a trusted middleman, a bank, keeping one central official record of who has what. But blockchain came along with a totally radical new idea, a way to do it with no central authority at all.
So the solution starts with this really wild idea, a shared public record book. Instead of just one bank holding the official ledger, what if everybody on the network had their own identical copy? This shared ledger is built out of what we call blocks.
A block is really just like a single page in that record book. It's basically a container that groups together a bunch of recent transactions. Alice pays Bob, Charlie pays David. You get the idea. But, a single page by itself isn't all that secure. The real magic is in how these pages, or blocks, are connected to each other. And this is the chain in blockchain. Every new block doesn't just list the new transactions, it also contains a unique cryptographic fingerprint. It's called a hash of the block that came right before it. This creates this incredibly secure, unbreakable link, literally chaining all the blocks together in perfect chronological order. Okay, so this structure creates an amazing self-defense system. Let's say somebody tries to go back and change an old transaction, maybe to take back a payment they made. The second they change even one tiny detail, the digital fingerprint of that block completely changes. And because the next block in the chain is still looking for the original fingerprint, that link between them instantly shatters. It's like a domino effect. That one broken link invalidates the entire rest of the chain, making the tampering super obvious to everyone on the network. So what is this digital fingerprint, this hash, that's doing all the heavy lifting for security? Well, this is where we get into a little bit of cryptographic magic. A hash function is basically an algorithm that can take any data at all. It could be the single number one or every book ever written, and it spits out a unique, fixed-length string of characters. And look at this, just changing the input from 1 to 2 gives you a completely different output. It's what we call deterministic. The same input will always give you the exact same hash. I love this quote from Gary Gensler at MIT because it's the perfect way to think about it. Just like your actual fingerprint is totally unique to you, a hash is a unique digital fingerprint for a piece of data. It's a super simple way to prove that nothing has been messed with. Now, for this whole system to be secure, these digital fingerprints have to be ridiculously tough. First, they're a total one-way street. You can't take the fingerprint and work backward to figure out what the original data was. And second, it's pretty much impossible to find two different sets of data that somehow create the exact same fingerprint. That's what makes them so unique and so secure. Okay, so we've got this tamper-evident chain of blocks. It's pretty cool. But in a network where nobody is in charge, that brings us to a huge question. Who actually gets to add the next block to the chain? Think about it. If anyone could just add a block whenever they wanted, what's to stop someone from creating a phony block filled with fake transactions that make them rich? The network needs some way to agree on what the single source of truth is. And that process is called a consensus model. It's just the set of rules that everyone in the network uses to reach an agreement. You can almost think of it as the blockchain's democratic process. All right, so the two most famous models are proof of work and proof of stake. Proof of work, which is what powers Bitcoin, is like this massive global math competition. Computers or miners all over the world are racing to solve a super complex puzzle. The first one to solve it gets to add the next block and gets a reward. The security here comes from the immense cost of all that computing power. Proof of stake is a totally different game. Instead of burning a ton of electricity, people lock up their own crypto as collateral. The more you stake, the higher your chance of being chosen to add the next block. With this one, security comes from having skin in the game. If you try to cheat, you could lose your own money. But here's the thing. Even with these really clever models, a decentralized system isn't bulletproof. The security is all based on certain assumptions about how people will act, and well, sometimes those assumptions can be challenged. And this isn't just a theory, we're talking about real money. In 2018, attackers found a weakness in the Verge cryptocurrency network and got away with about $1.8 million. So, how'd they pull that off?
They managed to pull off what's called a 51% attack. This is kind of the Achilles heel for a lot of proof-of-work systems. If one person or group can get control of more than half of the network's total computing power, they can basically bully the rest of the network. They can block new transactions from getting confirmed, and this is the scary part. They can reverse their own recent payments, which lets them spend the same coins twice.
And this brings up a really crucial point. You hear all the time that blockchains are immutable, like they're magically set in stone, but that's not strictly true. A much better way to describe them, as the National Institute of Standards and Technology points out, is that they are tamper-evident and tamper-resistant. The security doesn't come from making changes impossible, it comes from making changes so hard, so expensive, and so blindingly obvious that it's just not worth it for an attacker. So after all of that, why does any of this matter? Well, when you put all these pieces together, the chain of blocks, those cryptographic fingerprints, and the consensus models, you get something completely new. A powerful way to create trust in a world that is completely digital.
That same NIST report breaks it down into 4 pillars that make this trust possible. The ledger is append only, so it creates a permanent history. It's secured by cryptography, making it tamper-evident. It's shared, so everyone sees the same thing, and it's distributed across tons of computers, making it super resilient. Altogether, these pillars build a system where you can do business with someone you've never met without needing a bank in the middle.
But, and this is a huge but, it's so important to understand the trade-off here. Getting to this kind of decentralized trust is, as CoinDesk points out, incredibly inefficient. Think about it. Having thousands of computers all doing the exact same work is way slower and uses way more resources than just one central database. That cost only makes sense when the goal you're trying to achieve, decentralization, is absolutely necessary. And that really brings us to the final big question. In our digital world of global finance and data privacy, is this new way of creating trust, built on code and consensus, actually worth that huge cost in efficiency and energy? That, right there, is the multi-billion-dollar question that developers, huge companies, and entire industries are still trying to figure out.